Hello, dear students. Namshwaya. Namaste. Very happy evening to everyone. So yes, welcome to the day one of refresher course. So today we have with us Dr. Sreekala. She's currently working as Associate Professor, Department of Physical Sciences at our Amritapuri campus, which is in Kerala, Kollam. So she holds a PhD in the area of physics and she has more than 26 years of teaching experience in different colleges. So I take this opportunity to welcome ma'am towards today's session. Welcome ma'am, and we have a lot of students who are waiting for you. So she'll cover all your queries related to the topic, electric flux, statement of Gauss theorem and its applications. So welcoming ma'am to today's session and requesting all the children to just type whatever queries that you have in the chat box, and if there is anything else, you can ask for speak permission also. So yes, over to you, ma'am, and thank you so much for joining us.
My slide is visible?
Yes, ma'am. It's clear, ma'am.
Okay. Namaskar and good evening to all of you. So today we can start our session. Electric flux, Gauss law and its application. I am Dr. Sreekala, Associate Professor, Department of Physics, Amrita Vishwavidyapitham, Amritapuri. So in this session, just I am introducing the portions, electric lines of force and its characteristics, electric flux, electric dipole, Gauss law, and then application of Gauss law. So we can start with electric lines of force. I think you have already know about charges. So electric charges, two types of charges, positive charge and negative charge. So in order to represent these charges, these electric lines of force are introduced. Electric lines of force are just like that our magnetic lines of force. Magnetic lines of force are actually existing lines. So you can draw magnetic lines around a magnet using a compass needle. Compass and needle, you can draw the magnetic lines. That also it is visible. You use some iron filings over it, and then just tap the paper, then you can see nice pattern. These magnetic lines are actually existing. Magnetic lines analogy with the magnetic lines of force are introduced. Electric lines are imaginary. They are not actually existing, but they are imaginary lines. They are introduced to present the certain things, just like magnetics. Magnetic electric lines are lines and such a way that tangent.
Hello, ma'am. Just a second. I think a lot of students are typing in the chat box that your voice is breaking. Hello, ma'am.
Sir, lines. The tangent point of electric at point. They originate
Can you hear me?
positive, ends in negative. The number of lines in positive charge and the ending depend on the voice is not yet.
No, ma'am, it's breaking. I think a lot of children
Can you
are
hear
typing.
me?
Yes, I can hear you properly, but I don't know. Most of the students are typing. Voice is not clear. Voice is lagging.
And one problem is, Lakshmi, here just electricity gone. So I
Okay.
took the it from my phone. That may be the problem.
Okay, now it's clear, ma'am. Now it's clear, ma'am. I hope we can continue.
Okay. Okay. So these electric lines originate from positive charge and ends on a negative charge. The lines which are starting from the positive charge or ending on a negative charge depending on the magnitude of the charge. If magnitude increases, then the number of lines will also increase. So these lines never intersect. Intersection means if they intersect, there will be two values for the direction of electric field intensity, which we cannot, that direction of electric field intensity has two values, which is not at all, we cannot admit that one. At one point there will be only one value for electric field intensity. So that's why they never intersect. These are the characteristics of electric lines, of course. So what are electric lines? Electric lines are imaginary lines drawn around a charge, whether they are positive or negative charge, it is drawn then in such a way that the tangent at any point gives the direction of electric field intensity at that point. They originate from a positive charge and end on a negative charge. The charges originating from the positive charge or ending on the negative charge depends on the the magnitude of the charge. So they will never intersect. If they intersect, it means that there should be two values for electric field intensity, which is not at all possible. These are electric lines.
So, ma'am, there is a question. Why is electric field always perpendicular to the surface?
These electric fields are never perpendicular to a surface. We will come to that one. So I will explain you that what will happen. That is what I am explaining in the next one. That is electric flux. Electric flux. So in order to explain electric flux, we'll consider the first flow of a liquid. If a liquid is flowing with a velocity v through a small surface, let it be, if it is ds, then that is, if it is normal to a surface, then the rate of flow, rate means the flow divided by time, that is the volume of liquid flowing per second, that is called the rate of flow. Then rate of flow per unit volume or unit area per time is v into ds. If v is the velocity and ds is the area, then the ds is the area, then the rate of flow of the liquid is given by vds. So if it is normal to the surface or not parallel to the direction of the liquid, then but makes an angle with it, then projected area in a plane perpendicular to v is always ds cos theta. Area is cos theta. If it is not perpendicular to the plane, then we have to take the component, that will be ds cos theta. So in analogy with this, we'll explain the electric field. Electric field can also be electric field lines. Lines will also flow through a surface. So we define in analogy with this liquid flux. We can consider this as the electric flux. Electric flux is in analogy with the flow of the liquid. So that will be that electric flux through this area. You can see in this figure, you can just look to this figure, that sorry, this in this figure you can see that the electric field E, and this is the area, this rectangular portion. Can you see my pointer? I will take
Yes,
a
ma'am.
pointer here.
It's with
This is this line, this rectangular portion. This will indicate this surface, ds surface. So these electric field lines are going normal to this area, perpendicular to this area, normal to this plane, and these electric lines are parallel to the normal to the surface. Okay, normal to the surface and E are parallel. So in this case, we can write the electric flux lines. Electric flux lines are represented by delta phi is the electric flux flowing through a small area, that is delta phi. Delta phi is equal to E dot ds, or it can be called as E ds cos theta. E ds cos theta, because it is it is making, if it make an angle theta, here you can see, here it makes an angle theta to the surface, then electric flux is equal to E ds cos theta. So total flux is given by phi is equal to sigma E dot ds, or you can call it as integral E dot ds. Total flux is represented by the letter phi. Phi is the electric flux through a surface. Phi or suffix phi suffix E. Sometimes it is written as phi E, because magnetic field lines are also there. So magnetic field lines, it is represented by phi B. So that is phi is equal to sigma E dot ds, means E ds cos theta, or it is integral E dot ds. Integral is the, what is the difference between integral and sum? Integral is the continuous sum is called a integral. So unit of this electric flux, this electric field intensity, unit of electric dipole. Electric dipole is two equal and opposite charges separated by a small distance constitute an electric dipole. Two equal and opposite charges separated by very small distance. So usually it will be, sorry, let me take two equal and opposite charges. These charges should be separated by very small distance. This q is one of the charge, this is small q, and another minus q. So this q separated by very small distance. So this distance usually represented by the letter 2a. 2a. Why it is represented by 2a? Why can't it be a? Because always the measurement, this dipole is a single entity. So measurement is done from the center. So center is O. So that the distance from center to one of the charges will be A, and the other charge is A. So it is total distance is 2A. One moment, just give me 1 second, I am just coming.
Yes, student, kindly wait. I think there is a power issue that's happening there. Because of that only, her voice is breaking for some students. I am recording the session, so you'll be able to get it also.
Okay, so these charges plus q and minus q separated by a distance 2a, that is called a dipole. And this dipole moment is a physical quantity which represents a dipole. Dipole moment is represented by the letter P and is equal to 2aq. That is one of the charges into distance between the charges. Distance between the charges is 2a. So one of the charges into distance between the charges will give the dipole moment. P is equal to 2aq. It is a vector quantity and so it should have some direction. So direction is from minus q to plus q. The direction of P is from minus q to plus q. So it will be, so the dipole moment P is equal to 2aq. Its direction is from minus aq plus q and its unit is coulomb meter because q is coulomb and 2a is the distance. So it is coulomb meter is the dipole moment. Dipole moment unit is coulomb meter. Dipole moment unit is coulomb meter and its direction is from minus q to plus. Now, the electric field along the axis of a dipole. Here you can see a dipole minus q, this is minus q dipole and minus q charge and this is plus q charge. Okay, and it is distance between them is 2a. The direction is shown here as P. P is the from this blue line shows the direction of P. Now consider we want to find out the magnetic field intensity at the point P. So let me take a point here. So this we want to find out the electric field intensity at the point P. So to find out the electric field intensity at the point P, we have to consider these dipole as the two entities. That is one having plus q charge and the other is minus q charge. So we are considering it separately. So first we will find out electric field intensity at the point P due to plus q charge. Then we'll find out the electric field intensity due to minus q charge. Then add these two. So then you will get the total electric field intensity due to this dipole. So what we are considering a dipole, consider a dipole of dipole moment 2aq means dipole moment charge is q and then distance is 2a. So consider a dipole of dipole moment 2aq. In order to find out the electric field intensity at a point P, first consider the charge plus q and then consider the charge minus q, add these electric field intensities, then we will get the total electric field intensity at the point P. So here it is the vector sum. So E is equal to, since it is in bold, it means it is a vector. So E vector is equal to E plus E due to plus Q plus E due to minus Q. Okay. Now first we will find out the E due to plus Q charge. E due to plus Q charge is, you know, that electric field intensity due to a charge is equal to 1 by 4 pi epsilon 0 into Q by R square. R is the distance between the charge and the point. So here electric field intensity due to plus Q charge by 4 pi epsilon 0 into Q by R square. That is R is the distance between plus Q charge and the P. Here the P is at a distance R from the dipole, means center of the dipole. It is from the center of a dipole. So that center of a dipole means this center to the point P. P is center to Q is A. So from the center to the point P is R. So from this charge plus Q, to the point P will be R minus A. That's why here it is R minus A the whole square. Minus 1 by R plus A the whole square is for minus Q charge. So minus Q charge, it will be, it is from here, from this point, minus Q to P. That minus Q to P is R plus this distance. This distance is A. So it will be 1 by R plus A the whole square. So this the direction. Okay, that's why this P here. That is the direction. So this 1 by 4 pi epsilon 0, because we are here, why this minus sign came here? This is because when the direction due to plus Q charge is from the from left, from P to left side of the screen. So left side, and due to minus Q charge side. How will you find out the direction? In order to find out the direction, you place a positive charge here. Imagine you are placing a positive charge at the point P. If you place a point plus charge, unit positive charge there, the direction of movement of that positive charge. Due to this plus Q charge, the positive will be repelled. So the direction is found by that method. So this charge will move in this direction, that is towards the left of the screen. So that will be left of the screen, that is left side. And due to this plus Q charge, then due to minus Q charge, it will be along which direction? That is, you place a positive charge here, that this negative charge will attract this positive charge, so that this positive charge will move towards the negative charge. So this will be along the right side of this screen. Now, which will be greater? In order to add these two vector sum, in order to find this vector sum, will magnitude will be from larger magnitude to lesser magnitude. You will take the difference between the magnitude, and then direction will be the direction of the larger quantity. So the direction will be along this direction, that is from minus Q to plus Q, which is direction of P. Direction of P is from minus Q to plus Q, which is along the left side of the screen. So that is represented by this P here. That is, will give the direction P vector. This will give the, it is not the magnitude, it will represent only the direction. This P will represent only the direction. So that this is actually P unit vector P. So this will be the value will be first this value minus the second value, greater value minus magnitude, greater value minus lesser value. So 1 by R minus A the whole square minus 1 by R plus A the whole square. Now you take the LCM of these two values, then you will get R minus A the whole square into R plus A the whole square, which is R square minus A square the whole minus B the A plus B into A minus B is A square minus B square. Here one whole square is there. So R square minus A square the whole square. Then you do here, take the LCM, you will get here, it will be R plus A the whole square minus R minus A the whole square. So R plus A the whole square will be R square 2AB plus A 2RA plus A square, and here also this will give you minus. Then when you do that, you will get this 4AR as the center quantity. The other will be other quantity will be cancels out. That is, R square and A square will be cancels out. Only the adding component will be 4AR. So it will be 1 by 4 pi into 4AR into Q divided by R square minus A square the whole square. Direction is P vector. Direction is along the P direction of P. Now, since R is very much, if R is very much greater than A, then we can A square can be neglected. So we can write this as R raised to 4. This quantity R square minus A square the whole square can be written as R raised to 4, which will be, which this will be cancelled with this R, and you will get R cube. So 4AQ divided by 4 pi epsilon 0 into R cube, and direction is unit vector of P. Now we can write this 2AQ as P. including this direction also, magnitude, and you can write it as 2p. E is equal to 2p by r cube. So E is equal to 1 by 4 pi epsilon 0 into 2p by r cube. So you have to study like that only. Never cancel with these 4 and 2 and write, there is a tendency to write 1 by 2 pi epsilon 0 into p by r cube. Never write like that, because when you solve the problems, 1 by 4 pi epsilon 0 has the value 9 into 10 raised to 9. So you know that value. So always study like this: 1 by 4 pi epsilon 0 as a one quantity, single quantity. So 1 by 4 pi epsilon 0 into 2p by r cube, and p, the direction of E will be direction of P. Okay. Next, the dipole along the electric field. Yes.
Ma'am, can you just click the height that is showing in the, because students are saying they are not able to view the equation clearly. There will be a notification towards the end, something like stop sharing and hide. Hide. You have to just click on the hide.
Hide. Okay.
Okay. So, ma'am, just one
Yeah, E is
thing.
equal to,
I don't know whether this is related
1 by
what you are saying now. So there is a question like,
okay, ask.
shouldn't we subtract the both electric fields since they are in the opposite direction?
Actually, the vectors are not subtracted. Vector means it has to be added. Two vectors, addition of two vectors means if it is in the same direction, you can just add these two. If these two vectors are in opposite direction, magnitude will be subtracted and the direction will be direction of the larger vector. That's why subtraction came. Okay.
And even there is a question like
the
how
addition with a negative.
You are taking area as vector. How area is a vector? That is also a question.
Not area is not a vector. How area?
Okay,
where
it is
last
a question.
one?
No. It is a question by the student whether it's a vector or not. This one I think.
It is not a vector quantity. It is area. We are not taking as the area normal to the area as the direction. In order to show the, we have to. Oh, okay. Here, phi, isn't it? Phi. Phi is not a vector quantity, but area, this E and S, delta S. E is a vector quantity. Delta S here represent the vector quantity, means the normal to the area, the normal line. This line you can see as delta S. Delta S is the delta S here means that delta X vector means a vector quantity which is normal. That is, it never means that area is a vector quantity. Area is not a vector quantity, but the normal to the area is a vector quantity. Is it clear? So this normal to the area is we are taking as delta S. Delta S is not a vector quantity. Normal to the vector, normal to the area, vector quantity. Here delta S is a vector quantity because we are considering the normal vector this area. Okay, hope it is clear.
Yes, ma'am. I think we can.
Okay, next is electric field intensity along the equatorial line of a dipole. So here the equatorial line means the perpendicular line is called equatorial line. So it is here two vectors plus q and minus q. That is, sorry, two dipole, two charges. Consider a dipole with dipole moment 2aq, means dipole is charge is q and distance is 2a. So 2a, and let P be a point distant r from the dipole in the equatorial line of a dipole. Let P be a point along the equatorial line of a dipole. In order to find the electric field intensity at the equatorial line, we have to consider these charges plus Q and minus Q separately. So electric field due to plus Q charge is Q 1 by 4 pi epsilon 0 Q by R plus A the whole square, means this vector is R, this distance, this hypotenuse, that is R square plus A square. This distance is hypotenuse. So this is R square plus A square. So 1 by R square plus A square. So Q by 4 pi epsilon 0 into 1 by R square plus A square. Yes, correct. R square, this distance, this Q to P, distance is R square plus A square. That is the hypotenuse. Hypotenuse is this A root of A square plus R square. So here it is square of this quantity. That is, the root will goes and you will get R square plus A square. Because it is, we know that electric field intensity is 1 by 4 pi epsilon 0 into Q by R square. So here R square is R square plus A square. Okay, so due to minus Q charge also, this value is same value 1 by 4 pi epsilon 0 into Q by R square plus same value. Magnitude is same. But look to the direction. If you place a positive charge here, due to this plus Q charge, this positive charge will move along this direction. You can see this direction, that is along Q plus Q. Direction is away from this plus Q charge. And due to minus Q charge, this positive charge, so if you place a positive charge here, move towards this minus Q charge. That is this direction. So E minus Q. So E plus Q is there, E minus Q is there. Now we have to find out the resultant of these two quantities. So what will be the angle? These two will be angle between these two vectors. These two vectors will be here. This is theta. So this angle will be theta. This is also theta. So distance between these two angle will be cos 2 theta. Sorry, 2 theta. 2 theta will be the angle between these two vectors. So either you can solve this by parallelogram law of vector addition. Parallelogram law of vector addition, what you if two vectors are represented as the adjacent sides of the parallelogram, the resultant of the vector will give the diagonal of the vector will give the resultant vector. And if A and B are the two vectors, then the resultant vector R is equal to root of A square plus B square AB cos theta. That also you can use here. So here that vector will be, these two will be equal. So A and A will be equal. So the value will be root of A square plus 2AB cos 2 theta it will come. Okay. So A, and that you, from that you can take one A outside. So it will be E plus Q, that total vector will be 1 by 4 pi epsilon 0 into Q by R square plus A square, you can take it outside. Okay, that will be the vector E plus Q and E minus Q. Both will be 1 by 4 pi epsilon 0 into Q by R square plus A square. Then inside you will get that inside you will get a value cos 1 plus cos 2 theta, which is equal to 1 plus 2 cos 2 theta will be what? It will be sine square theta. Then take your root, you will get sine theta. Sine theta will be equal to opposite side divided by this hypotenuse. So opposite side will be R, and you will, sorry, that will be cos square theta, cos square theta, and you will get adjacent side divided by hypotenuse, that will be A divided by this, A divided by this hypotenuse. Hypotenuse will be root of R square plus A square. So adding that, you will get R square plus A square raised to 3 by. Then the numerator will be 2AQ. So this is unit vector. P unit vector. Okay, the direction will be direction of P, means from minus Q to plus Q, but it will be minus, that this direction of E is in this direction, which is opposite to P. P is from minus Q to plus Q. This vector E is along the right side of the screen, and here it is direction of P is from left side of the screen. So I have to give an minus sign here. So it will be minus of 2QA divided by 4 pi epsilon 0 into R square plus A square the whole raised to 3 by 2. Then if R is very much greater than A, then you can reduce these as R cube. So it will be minus 2QA divided by 4 pi epsilon 0 direction of P. So now 2AQ can be written as P, and this unit vector also given to that, it will be P vector minus P vector 1 by 4 pi epsilon 0 into P by R cube, which will be the electric field intensity along the equatorial line of a dipole.
Ma'am, just a second. Children are asking about the minus sign.
Dipole in a new, yes.
Why there is a negative sign? I think
Minus sign is because, yes, negative sign is, here you can see this dipole. Dipole, direction of dipole is from minus Q to plus Q. Shown here, direction of dipole. Okay, then the resultant of electric field intensity is along the right side of the screen. You can see here, that is, if two vectors are in this two direction with this angle 2 theta, then diagonal of this will give the resultant vector. That will be parallel to this dipole but opposite in direction. So that direction of E will be minus P. Is it clear? It is negative to electric field. The electric field, direction of electric field is opposite to the dipole moment P. Okay, you can see the direction here. It is from left, and for E it is right. That's why minus sign here. Dipole in a uniform electric field. So if you place, here you can see a dipole minus Q and plus Q charge, and they are placed in a uniform electric field. Electric field is uniform. That's why parallel lines you can see here as parallel lines. So if the angle between the electric field and this is theta, then a force will act on this minus Q charge placed in an electric field intensity E. So its force will be QE. So this QE will try to make this line make this dipole aligned in the direction of the field. So it will be, this is minus Q and plus Q charge. Force here will be QE, and here also plus QE. The plus Q will rotate it in the direction of the field. Here also minus Q will also rotate in the direction of the field. So that when it rotates, then the force acting on it is called a torque. Torque will be, torque equation, torque tau is equal to force into perpendicular distance between the forces. So here force is Q into E, and perpendicular distance is when it reaches these, that is the distance between these two charges, mean perpendicular distance, that is AN. AN is the distance here. Perpendicular distance is AN. AN will be, AN will be, that is, it is trying to make it in the direction of, so that will be 2A into, so that is equal to torque tau is equal to Q into 2E sin theta. So E sin theta, that can be written as 2A into Q as P E sin theta. So which can be written as P cross E. P cross E is the torque acting on this dipole. Now comes the Gauss law. Gauss law actually gives the relation between charge and the electric charge and the electric flux, relation between charge and electric flux. So here Gauss separately he assumed a Gaussian surface. Gaussian surface is an imaginary surface around a charge. So you can imagine any surface, but it should be closed. It should be, usually these surfaces are taken in such a way that it should reduce the complexity of the problem. So if around a positive charge, usually point charge, usually we will take a spherical Gaussian surface. If it is a line of charge, we will take a cylindrical Gaussian surface. Anyway, Gaussian surface is an imaginary surface which should be closed surface, and it is taken in such a way that it should reduce the complexity of the problem. One moment. Okay, so Gauss law states that the total, it is using this Gauss law, you can solve the problems very easily. So Gauss law states that the electric flux through a surface, Gaussian surface is a surface which is a closed surface. So electric flux around a closed surface is directly proportional to the charge enclosed, or it is equal to 1 by epsilon 0 times the charge enclosed. So correctly speaking, the electric flux through a surface is equal to 1 by epsilon 0 times the charge enclosed. That is electric flux. How will you find out the electric flux? Using the relation integral E dot ds. So integral E dot ds is equal to 1 by epsilon 0 times the charge enclosed. So Gauss law states that the electric flux around a closed Gaussian surface. This is the statement of the Gauss law. Gauss law states that the electric flux around a through a electric flux lines through a closed Gaussian surface, or Gaussian surface is enough because Gaussian surface is always a closed surface. Total electric flux through a Gaussian surface is equal to epsilon 0 times the charge enclosed. If it is not a free space, then you have to take it as 1 by epsilon 0 times the total charge enclosed by the Gaussian surface. Charge enclosed by the Gaussian surface. Gauss law states that the total electric flux through a Gaussian surface is equal to 1 by epsilon 0 times the charge enclosed by the Gaussian surface. That is Gauss law. From the Gauss law, you can find out the Coulomb's law, or this can be reverse also. You can find the reverse also. Anyway, Gauss law and Coulomb's law will relate. So for that, consider a charge plus Q. Then, in order to find out the electric field intensity at a point P on the surface, which is at a distance r from this charge Q, consider a spherical Gaussian surface around the point P, around the charge Q through the point P. Okay, in order to find out the electric field intensity at the point P, then what you have to do is you have to consider a spherical Gaussian surface around the charge Q, including the point P on the surface of that Gaussian surface. Okay, now we can find out the total electric flux through this Gaussian surface. Total electric flux through the Gaussian surface is given by integral E dot dA. So integral E dot, according to Gauss theorem, we know that the integral E dot dA is equal to phi is equal to 1 by epsilon 0 times the charge enclosed, or 1 by epsilon 0 into integral E dot dA is equal to charge enclosed. Then here, for this charge at the center, all field lines will be normal to this spherical surface, so that this dA can be written as E into dA, because the normal and these lines, this is also normal. So the angle theta is 0 So it will be cos 0 is 1. So it will be E dA. So epsilon 0 times integral is no issue in that one. Now how will you, this electric field intensity is constant. So you can take it outside, integral dA. Integral dA means the area, surface area of the whole sphere. Surface area of the sphere of radius r is 4 pi r square. So that you can write epsilon 0 E 4 pi r square is equal to Q, or E is equal to 1 by 4 pi epsilon 0 into Q by r square, which is the electric field intensity. If one more charge is there, then you can find out this Q1, Q2 force will be, you can find out the force also. Then that will be Coulomb's law, which is F equal to 1 by 4 pi epsilon 0 into Q1, Q2 by r square. Now, application of this Gauss law. You can find out the electric field due to an infinitely long, straight, uniformly charged wire. So consider infinitely long, uniformly charged wire of linear charge density lambda. Lambda is the linear charge density, means charge per unit length is called uh, linear charge density. Charge per unit length is called a linear charge density, lambda. So consider a infinitely long straight conductor of charge linear charge density lambda. Okay, to find the electric field intensity at a point on the surface of at a point a point P, which is distant r from this line of charge, then construct a cylindrical Gaussian surface of radius r and length L. We are taking a length L. So consider a cylindrical Gaussian surface of radius r and length L with the point P at the surface, surface of the cylinder. Now, cylinder is having how many area surface? 3 surfaces are there. 2 base surface and then 1 curved surface. So, base surface dA1 represented as dA1, then another base surface as dA3, then curved surface as dA2. We know that these electric field lines from these charges will be normal to the curved surface, and it is perpendicular to the this base surface. So with dA1 and dA3, these electric field lines will be perpendicular, so that the angle will be 90. So the flux through that surface is 0. There is no electric lines through the area perpendicular to dA1 and dA3. Electric lines are passing perpendicular to the curved surface only. So the total electric flux is given by integral E dot dA1, E dot dA2, E dot dA3. Among these, E dot dA1 is 0, E dot dA3 is 0, since the angle is theta is 90 degree. Okay. So here E dot dA3, sorry, dA2, E dot dA2 is E into dA2, E into dA2. Sorry, this is dA2. Some mistake happened. So this is dA2. So dA2. Integral dA2 is area of the curved surface. Area of the curved surface of the cylinder. The area of the curved surface of the cylinder is area length into it. When it is open, it will be a rectangle, and you will get so this area is dA2. dA2 into E into 2 pi RL. So by Gauss law, we know that E into 2 pi RL is equal to pi epsilon 0. So E is equal to Q by 2 pi RL into epsilon 0. Or this Q is the charge in this charge enclosed by the Gaussian surface. This is infinitely long long line of charge. So with the line linear charge density lambda. So that the total charge enclosed by this Gaussian surface will be lambda into L. So lambda into L divided by, instead of Q, you can write lambda into L. So this L and this L cancels. So you will get 1 by 2 pi epsilon 0 into lambda by R. And the direction will be direction of R. So that is why it is written as R cap. R cap is the unit vector along R. That is out of the curved surface. Is it clear? Next is field due to an uniformly charged infinite plane sheet of charge. So we are considering an infinite plane sheet of charge with plus sigma is the surface charge density. Sigma is the surface charge density, means charge per unit area, that is called a surface charge density. So in order to find the electric field intensity at a point P, which is very near to this conductor. So this is a infinitely long charge sheet. So we are, in order to find the electric field intensity at the point P, which is very near, this R is very, very small, very near to the conductor, then consider a cylindrical Gaussian surface with charge at charge in one of the faces, one of the it is in the base surface, in one of the base surface. Consider a cylindrical Gaussian surface such a way that the point P is in the base surface. Okay, or either you can consider a cylindrical Gaussian surface or you can consider a rectangular Gaussian surface. Both are equal, both are same. If you consider rectangular also, this you can derive this relation. That is, it should contain, the base portion should contain the charge. Okay. Now, you can apply the Gauss theorem here. Gauss theorem, in order to Gauss electric flux of phi epsilon 0 times the charge enclosed. So phi is equal to integral E dot dA. So here, if this area, this surface is having an area A, this surface is having this curved surface, not curved surface, this base surface is having an area A, then since this is a very thin sheet of charge, the electric field lines positive from this positive charge will be in both the direction. That is normal to the surface. It will go in this direction, also in out of this plane, in both the directions. So the area will be A, this side A, and the left side also one more A is there. So the the Gaussian surface is separating these two sheet into the sheet should pass through the center of the Gaussian surface. The line of charge, this area of the charge will be thin sheet of charge should pass through the center of the Gaussian surface. Okay, so that both the surfaces are there. So E dot dA into plus E dot dA. So 2E into A, because angle theta is 0. So it will be EA. 2EA is equal to charge will be sigma into A, because sigma is the surface charge density. A is the area, then it will be sigma into A will be the total charge divided by epsilon 0. So E is equal to sigma by 2 epsilon 0. N cap is the direction, that is from out of the plane of the paper or this plane, that surface charge, the thin sheet of charge, out of the thin sheet of charge, that is the unit vector n cap. So E is equal to sigma by 2 epsilon 0. It is very, very important. This can be applied to a thin sheet of charge. What will happen to this sheet is thick? If this sheet is very thick, what will happen? This Gaussian surface will go, one of the Gaussian surface will go inside. Okay, so that it will be, the Gaussian surface will be inside this sheet. If it is thick sheet of charge, then the line of the electric lines will pass through only through one surface. So there, this will be EDA only, because it is a thick sheet of charge. So epsilon 0 into EA is equal to sigma into A. So that E is equal to sigma by epsilon 0. So electric field intensity is given by sigma by epsilon 0 for a thick sheet of charge. For a thin sheet of charge, it will be sigma by 2 epsilon 0. So this all about this chapter. So what we have covered is electric lines of force. Electric lines of force are, what are electric lines of force? They are imaginary lines drawn in such a way that the tangent at any point gives the direction of electric field intensity at this point. Then these electric lines, characteristics of electric lines. What are the characteristics of electric lines? These electric lines originate from a positive charge and ending on a negative charge. The number of lines originating or ending depends on the magnitude of the charge. Then these lines will never intersect. If they intersect, it means that there are two values for electric field intensity, which is not at all possible. So they will never intersect. Then electric flux. Electric flux is the number of electric lines of force passing normal to a surface. Number of electric lines of force passing normal to a surface is called the electric flux. Then comes the Gauss law. So before Gauss law, the electric dipole is two equal and opposite charges separated by a very small distance constitute a dipole. Then we gone through the electric field intensity due to a dipole along the axial line. It will be 2p by 1 by 4 pi epsilon 0 into 2p by r cube. Along the equatorial line, it will be minus 1 by 4 pi epsilon 0 into p by r cube. Then dipole in an uniform electric field, torque acting on an electric dipole is P cross E. Then Gauss law states that total electric flux along a through a closed Gaussian surface is equal to 1 by epsilon 0 times the charge enclosed. This is very, very important law. Using this, we can easily derive the equation for a electric field intensity at a point near a point charge, and also we can find out the electric field intensity due to a line of charge. That will be 1 by 2 pi epsilon 0 into lambda by r. And then you can find out the electric field intensity due to a thin sheet of charge. It will be sigma by 2 epsilon 0. And for a thick sheet of charge, which will be sigma by epsilon 0. If you have any queries, you can ask.
Actually, there are a lot of queries. I think I'll read out so that it will be helpful. So actually, what will happen when there is continuous change in electric flux?
Continuous change in electric flux means the charge should vary. That is, if variation in electric flux means we have to pump some electric charges on that. If electric charges varies, the charge density varies, then electric flux varies. But in that cases is little bit complicated cases. That one is not here, not for your for the time being, not for you, not applicable for you.
Okay. Now, is volume charge density charge per volume?
Charge per, yes, correct.
Okay.
Volume
Then,
charge density is charge per volume.
Okay. So there is one more question. Is linear charge
divided by volume?
They have asked charge per length.
Charge per length.
Okay.
Charge divided by length is charge divided by length is this linear charge density. Okay. Charge divided by area means volume. Sorry, what is called it is a charge divided by area is surface charge density. Then charge divided by volume, it is represented by the letter rho. That is called volume charge density.
Okay. So for all the students who are typing, will you get the materials? We'll be providing the materials. We'll be providing the recordings. All these will be provided. We'll be updating you over mail, and also we'll update in the Telegram group available. Okay. Now, okay. If the charge is in, okay, there are a lot of questions coming up. If the charge is in the center point surrounded by either a sphere or a cube, is the flux at the surface is different in two cases? What if in a
Which
cube it is asked, or for flux if it's in a square face?
uh, um, if it is if there is a charge at the center, if you consider a spherical Gaussian surface or a rectangular Gaussian sorry, or a cubical Gaussian surface, any surface around that charge, the electric flux will be same. It won't change. How much large you will take, then also the electric flux remains same.
Can the Gaussian surface be of any shape?
Any shape.
Okay.
But that Gaussian surface is, because it is imaginary surface, we are selecting that surface. It should be like that. It should reduce the complexity of our problem.
Okay. Ma'am, there is another question. Electric field at the axial is equal to 2 times electric field at the equatorial. So is it necessary to consider negative sign in this relation? Do we have to consider negative sign?
Yes, because electric field is direction is very important in the case of electric field. So negative sign is important.
Huh. Why can't the electric field lines be inclined at an acute angle with the base of the Gaussian cylinder in case of a straight conductor? Why can't the electric field lines be inclined at an acute angle with the base of the Gaussian cylinder in case of a straight conductor?
Straight conductor, we are taking it, the cylinder, we have the choice of selecting the Gaussian surface. We are selecting, cunningly we are selecting the Gaussian surface in such a way that that is we are selecting a cylindrical Gaussian surface in such a way that that angle between the electric field line and the base is 0.
Okay.
That line between the this not the normal, I am saying normal to that and the electric field is 90 degree. Base and the electric field is 0. So that normal and the electric field is 90 degree. We are selecting like that.
Okay.
We don't want to make an angle because it will make the problem more complex.
So ma'am, there is one more question. Any real life applications of Gauss law for better understanding? Anything?
Real life problem.
Applications or something, that's what. I don't know.
Applications are there. Applications are there. That is in that is what is called Van de Graaff generator. Heard about Van de Graaff generator? Van de Graaff generator is an equipment which will produce lot of charges. Charges can be produced, maximum charges can be produced on the surface of a conductor by pumping it from the base. That is, this Van de Graaff generator is for making these charges. We are accelerating charges. One example that you know this one. What is that? Particle accelerators. You studied about nuclear fission and fusion. So in nuclear fission, this has to be this uranium has to be bombarded with an alpha particle or for nuclear fission neutron. So these charges, so suppose if it is an alpha particle is having positive charge. This charges has to be accelerated. For this acceleration, for particle accelerators, we can apply this theory. So it is there. Lot of examples are there.
Actually, what is
some examples I will write and then.
Okay, ma'am. I'll give it to the children in their groups.
Yes.
What is n cap unit vector's direction?
Unit vector means a vector which is having a particular direction and its magnitude is 1. Okay, direction is the direction of that quantity. Example, P cap means direction of P, and it is not having any magnitude. Magnitude is 1. So direction of P is from minus Q to plus Q.
Okay.
So P cap means direction. Then I cap is there. I cap, J cap, K cap. Direction of a vector along X direction is I cap, which is unit vector. J cap means along Y direction. Z cap means, sorry, K cap means along Z direction. N cap means a normal vector. Normal to a something, that is called a n cap.
Okay. In the linear charge density, there is a component called dA1 and dA3. They are getting cancelled. And why isn't there an opposite direction for the vector dA2?
dA2 is the area, the curved portion. So in curved portion, the normal to the curve and the electric field, they are in the same direction. So angle is 0 there. So E dot dA is E dot into area is E dA cos theta. Theta is 0 there. Cos 0 is 1. That's why. The other portion, angle is, it is normal to that surface. Normal to the area and the electric field. Both are perpendicular to each other. So angle is 90 there. So it is 0.
Why is the area vector is always outside the surface of the body? Why not inside the surface?
Um, that is
No,
a
it's
question.
like
Very interesting question.
no, no,
But
I think
actually,
most of them are preparing for those days only. So they are like, huh. And even there
so
are children. Yes, ma'am. Yes, ma'am.
yes, surface. So here we are not considering the surface. We are considering normal to the surface. Okay, normal to the surface means this electric field normal. DS means it is not area vector. It is a normal to the area vector. Okay, normal. Normal is actually we are considering it is outward, because the Gaussian in all the Gaussian surface, the we are what is that? Gauss law states that electric field, total electric flux, and through a Gaussian surface, total electric flux through a Gaussian surface is equal to 1 by epsilon 0 times charge enclosed. Means the total electric flux coming out of the Gaussian surface. Okay, suppose you are placing a negative charge there inside. Here in all the cases we considered only positive charges. Suppose a negative charge is there, then what will happen? The electric flux lines goes into that. Okay, in that case we will take normal and the electric flux lines are anti-parallel. There we will take it as 180 degree, cos 180 degree. Okay, cos 180 degree means minus 1. It will come as minus 1. So this normal to a surface is always outwards in that normal to a surface. But electric flux can be opposite direction also, inside also. Normal to a surface means it is always outward.
So, ma'am, there is actually a lot of students are requesting for. Will you be able to explain that thick sheet, that concept again?
Thick sheet.
Huh.
Uh,
And there are questions that in the thick sheet, why is it sigma? Why is it not epsilon?
eh?
Why thick sheet electric field? I think it's regarding the values. Can you please expand the question that you've typed?
One more. How
I
can
have
I
asked the
show
child.
the
I
slide?
think he'll.
Now I will share screen. Okay, share the screen
Okay,
once
okay,
again.
okay, ma'am.
Is it visible? Screen is visible, Lakshmi?
No, ma'am, actually.
No. Okay. One moment.
Okay.
It is not shared. Share.
Yeah. Now the slides are visible, ma'am.
Okay. This is a thin sheet of charge. Imagine this as a paper, one paper of your notebook. Okay. Then when you take a point very near to the, that's I will take a pointer also. Sorry. So we take consider a paper. Then this Gaussian surface is cylindrical one, and it is passing. That point is, though it is shown r like this, actually this point distance r is very small, very near to the charge. The point P is very near to that sheet. So you are considering a thin sheet as a paper, as a thin sheet, then a this Gaussian surface, cylindrical Gaussian surface like this, smaller one. Okay. Then if it is a notebook, take a notebook and put it here, then it will be very thick one. Okay. Then this surface will go inside that book. One surface will go inside the book. So Gaussian surface, when you consider this will go inside. So the charges are always in the surface. So this Gaussian surface will be one side, you will get only one side only. The other side will be inside that book. For a thick conductor, when you charge a thick conductor, the charges will stay only on the surface. That's why here it is 2 epsilon 0, 2 times 2 into EDA, because it has two surfaces for the thin sheet of charge. If it become a thick sheet, then this surface goes into this thick sheet of charge, and you are left with only one Gaussian surface. So for that Gaussian surface, it will be epsilon 0 into EA. EA is the total flux, EA. That's why it will come as sigma by epsilon 0. Is it clear? If it is clear, type yes. Otherwise,
yes, ma'am. It's they have already written thank you. We were able to clear a lot of queries that was not answered in classroom. So they are typing like that. So,
okay.
ma'am, just a few queries I think we'll be able to take.
Hmm.
If point charge Q is placed at the center of a spherical shell of radius r, the shell is made of dielectric material with a dielectric constant K. How we will be calculating the electric flux through the spherical shell?
Okay. Then it will be this is the equation. So it will be 1 by 4 pi epsilon 0 into K, Q by R square. K is the dielectric constant of the medium in which the charges is placed. Dielectric constant of the medium in which charges are placed. So it will be 1 by 4 pi epsilon 0 into K into Q by R square. K is the dielectric constant.
Ma'am, there is one more question. We know that electric field is directly proportional to 1 by r square, and in dipole it is 1 by r cube. So potential difference is like directly proportional to 1 by r. Similarly, in dipole 1 by r cube. So it's like why electric field and potential difference is same in dipole.
Potential it is r square.
Okay, so I think they have mentioned
potential is the next before capacitor next portion. So in that potential, this is this for a dipole. Potential is r square. It will come as r square. P by r square.
In the case of torque on dipole and external field, if the angle is 0 degree and 180 degree, Sine theta equal to 0, torque equal to 0. Is there any difference between both the cases?
Yes, both the cases, one is the one will be magnitude will be positive and the other will be minus negative, because this charge has to come all along with, it has to be, this dipole has to align in the direction of the field. Usually if water, you take water current, in a water current if you place a stick just perpendicular to it, first you can see this stick will align in the direction of the water current and then flows along with that. At that time, the energy will be minimum. That's why it is rotating in the direction of this water flow. Like that, in electric field also, if you place a charge that is dipole, it will align in the direction of the field. If it is 0, it will align like that. Then if it is 180, it will align in the opposite direction, turn in completely in opposite direction. Complete one rotation it will go. That's why it becomes magnitude will be minus.
Okay. There are questions like why we are not able to extend the Gaussian surface. It's like we have considered it inside the thick sheet and all. So why we are not able to extend it?
You can extend, but we are there, we are finding the electric field intensity very near to a plain sheet of charge, because the application of this comes in capacitors. So capacitor, two electric plates are there in a capacitor. You have seen capacitor, paper capacitor, very thin paper capacitor. In that, two electric plates are, one paper is kept in between the two electric plates. So that much distance is there in between the plates. So you have to find out the potential there. So in order to find out the potential, you need the electric field intensity at that point. So in order to find the electric field intensity very near to that plain sheet of charge, we are using that very small cylindrical surface. So that this surface we can select as our own choice. That's why it is an imaginary surface. So this electric plain sheet of charge you are studying for parallel plate capacitor. Application comes next.
Okay.
Next
Ma'am,
chapter.
I think we'll just take one more question because we have extended half an hour more. Why electric field is zero inside a spherical shell but not zero inside a solid conductor?
Solid electric shell
Yeah.
of shell means is it a conductor?
That is what.
Charge is, if it is, charge is not there inside a conductor. If how thick the conductor or a shell, the charge will be only on the surface. If it is a conductor, charge will reside only on the surface. So there is no charge inside. So it will be, the electric field will be 0. If it is charge is there, then only it will have an electric field. May I know question once again?
It is like why electric field is zero inside spherical shell but not zero inside a solid conductor. That's what it is.
Solid conductor.
Yeah, they have just written solid conductor. If the student is here, just you can update it, I think. Okay. Or if there are any further queries, I would request the children, we'll send you a link and we'll collect it and we'll get it solved. Okay. So we have already extended half an hour. So thank you so much, ma'am, for coming. And I think they have already mentioned that they were able to clear a lot of queries that were not answered in classes.
Okay.
So I hope they got an opportunity. Yeah.
The main problem with the class that they don't know actually. The main problem is the class, their time limit is very less. Time is very less, so they have to rush through this. So that's why. That's the main problem. In class also, we'll do like this only.
So thank you so much, children. So tomorrow we have a max session. Yes, I think you can just look at the chat box, ma'am.
Okay. Thank you
So
very
thank
much.
you so much, everyone, children. And once again, thank you to Sreekala ma'am for especially coming and also extending more than half an hour. clearing all the queries. And they are also mentioning they were able to understand, clear all the queries. It was super teaching and all of them. Thank you, children. Thank you, everyone. And thank you so much. And I have a very good evening. Namaste. Thank you. Thank you, ma'am. Thank you so much.